Welcome everybody, it's your favorite AP Physics teacher and your only AP Physics teacher, Dr. Bonner here, and boy do we have a good one for you today. I know I say that about all the videos, but this one's really fundamental and you get to just draw diagrams all day, so drawing is pretty fun. Let's get right to it. The first thing we're going to do is go through the different types of forces you're going to see here in the mechanics semester and how to diagram them. So the first one we're going to look at here is going to be force tension. So as a quick variable note, back since around the 2000s or so, physics has started to use F, which is capital F for force, and then a subscript for the type of force that we're talking about. In this case, tension would be T. Prior to that, it was very typical to just use capital T for tension or like a single variable. And that's still true in a lot of the multiple choice, but you'll probably see this capital F with a subscript. Either is fine. If they give you a variable as a given for tension or any force, just use the given variable as always. So with tension, it's any pulling force, literally anything. So we're going to draw it from the point of contact, meaning the object is going to be getting pulled by contact with something, and you can just draw it right along that object. Whether it's a string, cord, rope, cable, or it can even be like someone's hand grabbing and pulling as well, any pulling force. So in our example here, we're going to use some strings. So we have point of contact up along the string, a horizontal string, point of contact along the string, and an angled string, again, where the string is attached and along the string. So nothing too fancy there. And if you have a pull, then we should also have a push. So push in more technical terms would be referred to as an applied force. And you may see capital F with APP for applied force. Again, they're kind of synonyms. And we're going to be drawing them from the point of contact away. A common theme throughout all these force diagrams is draw it from the point of contact and then directly away from the object. All forces will have a point of contact except what we call field forces, and the one of importance here in this semester is gravity. Okay, and we'll talk about that here in a moment. So in pushing, let's talk about then the two objects involved here especially. So this is a picture from way back, I think it was like 2006. We got Scott and Jim. Those are my former students, so I don't know if they realize they'd be immortalized into an example here, but if you're watching, Scott or Jim, hello, reach out, say hi. We're going to focus in on Jim since he's in the front there. He's in the green shirt, and he's pushing this car. And yes, this is our school parking lot. It looks way different now than it did back in 2006. So we have two cars involved. We have two objects involved, this black car and Jim in the green shirt. We'll just disregard Scott here for a moment. Now if I draw those, I have to draw them separately. Am I looking at the forces acting on Jim, or am I looking at the forces acting on the car? They have to be drawn separately in this case. So the point of contact between those two would be where the yellow dot is. And the question I want you to chew on here for a second is going to be which way would we draw that force push that's acting on Jim, and which way would we draw the arrow for the force push acting on the car? Go ahead and think about it. You can pause. Great. They would actually point in this way. Let's look at Jim first. Jim is not getting pulled by the car. He's actually getting pushed against, right? His hands, which would be to the left, and the car is getting pushed to the right. If you think about the way it's feeling a push, it would be to the right. So these are always going to be equal and opposite when you have forces between two objects. So for example, this arrow would be the force acting on Jim, which is why we drew it on Jim's diagram, by the car. If we flip those, meaning what is the force on the car by Jim, then now we're looking at the car. What are the forces on the car, for example, right? And so this arrow represents sort of the tails of this coin, where if you have a heads and tails of the same push force, they are equal and opposite. That's Newton's third law coming soon. The car's force is going to be pushed to the right. So again, force on the car by Jim to the right, force on Jim by the car to the left. See how those are like flip-flopped. Moving right along, a third force is that force of gravity. So we have force gravity. A lot of times we'll just use what force gravity is equal to, which is mass times gravity, which is that 9.8, or what we commonly use as just 10 in physics. That one single variable that we can use instead of Fg would be W, because force, gravity, and weight are synonyms. So another way of writing this force gravity equals mg equation would be to use that W for weight as the variable instead of Fg. So that's, again, interchangeable, but more of an old school way to do things. So with gravity, because there's no point of contact, we're just going to draw the arrow for force of gravity, starting at the beginning of the center of mass and then pointing straight down towards the center of the Earth. Very important, towards the center of the Earth, not just down, but down towards the center of the Earth. We'll show you some examples of where that can get a little confusing. Normal force. Okay, so normal force does not mean typical, ordinary, or common. Normal force is a math term, which means perpendicular to a curve, or in this case, perpendicular to a surface. Okay, so normal lines in math are lines that lie perpendicular to a surface or a curve. So here's a curve. You can see this black polynomial curve. And if I look at some point here in red, and I draw a normal line going through that point, you can see that this red line is perpendicular to the curve. And I can show you how this would then change as we go along the curve. So at the very top, imagine this were like a hill. Normal force would be pointing up, away from the surface. If it were on a tilted surface like this, normal force would point perpendicularly away from the surface at all times. So that's the axis along which the normal force resides, and it represents the force from that surface pushing against an object that's touching it. So for example, we had this curve we just looked at, but we also have a lot of flat surfaces often, right? And so we have normal force. You can see there's that N that they have for normal force 1. Here's a normal force 2. It can go either way depending if you're upside down or just flatten the surface standing up. This is often used in what we call optics, where you have a light ray that's coming in, maybe like from the sun, and that angle that it comes in at, if it's hitting a solar panel, for example, it's here, the surface of the solar panel is going to be directed in a way that's going to have a normal line that's going to be tilted but perpendicular to it. You can see here by a dotted line, that's the normal line, and we measure our angles of those incoming light rays from there. And we could have a sphere, right? Just like planet Earth, and the normal force is going to point directly away, just like it would any other curve, so that it's perpendicular to the surface. Normal force represents, as we said, contact with that surface. So if you have touching or contact with the surface, then you will have a normal force. It's going to point from the point of contact with that surface perpendicularly away, as we said. So some examples of where you see this, drawing from a side view. There's your point of contact. Draw it away, Fn. If it's a tilted surface, as we talked about, then you would have a tilted normal force, so that's perpendicular to the surface. And again, we can also call this capital N as well if we wanted to. Either one's okay. What if it's touching two surfaces? Then we would have 2 points of contact and 2 different normal forces, which we can use the subscript 1 and 2, Fn1, Fn2, to show those 2 different normal forces. Lastly, what we're going to look at for this semester is going to be the force of friction. And so instead of being a perpendicular force from the surface, this is going to go along the surface, so parallel to that surface. It's going to point opposite the way it is sliding, or opposite the way it would slide if friction weren't present. So therefore, there's 2 different versions of friction. There's when it's not sliding, which we call static friction, and when it is sliding, which we would call kinetic friction. Okay, so static friction and kinetic friction are always going to point opposite the way it is sliding or would slide. And so if sliding is the key here, it's not which way it's moving necessarily, it's which way it is sliding or would slide. And that's always a good way to try and determine which way friction's pointing. We're going to look at a couple examples here that is based on what students mess up often when they're first learning this stuff. So let's take a look at A and see if we agree with it or disagree. So this is what I see a lot. So normal force going perpendicular surface, gravity going down into the surface. And we're using mg as gravity instead of Fg because they're equal. So is this correct? No, this isn't correct because gravity should be drawn straight down to the center of the Earth. Remember, that's that tricky thing we have to look out for. So what about B? In this case, we have gravity straight down and normal force straight up. That is something we often see, but that's for flat surfaces. And if you look here, is this right? No, because normal force is not perpendicular to the surface like it has to be. And so the correct way to do this would be to draw normal force going perpendicular to the surface and gravity straight down. And so you see here, this would be the example that we want to use, and it'd be like, yay, this is what we want. Last thing we're going to look at with this video is going to be the difference between drawing a force diagram like we've been doing and what we often use in AP as a simplified way to do things, which is a free body diagram. Okay, so to compare and contrast these in force diagrams, as always, we draw the arrows from their points of contact away. This is really good conceptually because it helps to anchor these forces as acting from points of contact. And this ends up being the way we want to do this for rotational problems where these forces are causing twists, or what in physics we call a torque. Free body diagrams are just drawn from the object center. So we abbreviate the object as a point, maybe at its center, right? And we draw all the forces acting on the object's center of mass. This is a simplified diagramming. This resembles a lot of what we would do with vectors from pre-calculus, especially, and into calculus. This way you'll see a grid, as we're going to do an example here in a moment, that can be provided to you where you show then longer arrows to represent stronger forces or larger magnitudes. So let's look at some examples here. So first example, we'll look at a block that's being accelerated with friction, but since it's accelerating as it's being pulled, then the tension force that's pulling is going to be greater than the frictional force. So let's go ahead and draw the force diagram. So we have gravity, normal force, tension, and friction. And because it's sliding, this would be kinetic friction. If we want to draw a free body diagram of this, we would just draw this object as that dot. So it's kind of like this dot we have here. We're just going to draw it right there. And then we're going to draw all of these arrows, instead of acting at points of contact, we're going to draw all of them acting on the object as a dot. And so now you can see it's a simplified view of this. We can see the opposing forces easily. And if we were to draw this on a grid, on an AP exam, I would just want to redraw what we have here, but paying special attention to make sure that all the lengths of the arrows are correct relative to each other. So longer for stronger ones than the opposing forces, or same if they're supposed to be balanced. So I'm choosing to make this downward force of gravity 2 boxes. I could have chosen 1 or 3, but you want to do this one first as a working diagram so you can figure out what forces are there and start to compare the forces so we know which one to draw, so we can pick and choose how many boxes to represent. Let me show you what I mean. If I choose 2 boxes here, then I know that normal force is balanced and is going to have to be 2 boxes as well. Now for tension, I know this arrow to the right has to be greater than friction. So however many boxes I choose to the right, I want to show that it's bigger than friction, which is the arrow to the left. There's no way for me to know if there's 2 boxes, for the vertical forces, and how that tension would compare to it, so it doesn't really matter there. But I'm just going to go ahead and choose 3 boxes for tension, which means I need to use 1 or 2 boxes for friction. I'll choose 1 here to show that there's more force to the right than to the left. Oops, on this block that's sliding at a constant speed down here. So it's a constant speed as it's pulled, so that means that there's balanced forces. So I'm going to draw my force diagram first from points of contact, which would mean that we have a downward force of gravity, an upward normal force, angled tension force, and a force of kinetic friction to the left. On a free body diagram, I'd redraw those points of that center point, and then draw all my arrows from that single dot here in the middle. So we'd have our tension, gravity, normal force, and friction there. Now this is where we have to be careful. Now that I've done my little working copy here off to the side, if I want to try and draw these as having relative magnitudes, meaning longer, more boxes for stronger arrows, then I have to realize that this angled force, if I make it, let's just make it 2 diagonal boxes, then to the right, it's spanning a horizontal 2-box length, which means that that x-axis 2 boxes length, you can think of it as the x component of its right triangle, has to be balanced with this leftward arrow of tension. So that angled tension, which can be the hypotenuse of a right triangle, we need then the horizontal component to balance out with friction because it's balanced forces. So I need to make sure 2 boxes left, 2 boxes right. And that 2 boxes right has to be the x component of a right triangle. Now I got to be careful because I have the angled tension is producing an upward force of 2 boxes in length. So I got to make sure that all of my upward arrows and all of my downward arrows balance out. So I have an upward arrow here of 2, I have an upward arrow of gravity, and I have a single arrow down. I'm sorry, I said that wrong. I have an upward arrow of tension. I have an upward arrow normal force. So I have 2 upward arrows, right? The tension Y and normal force, and then a single force of gravity down. So I'm going to make gravity 3 boxes total, so that I can do 2 up for tension and 1 for normal force. So now you can see here that I have 2 boxes up, that's the vertical tension, 1 box up for normal, that's 3 total boxes of upward force, so we have 3 total boxes of downward force. It's a little tricky one at the end, but shouldn't be too much of a problem. Thanks everybody, have a good one.